In the vast realm of physics, where the mysteries of your universe unfold, quantum field theory stands as one of the most profound frameworks. It is a theory that does not just describe particles, but fields, endless, invisible webs stretching across space and time. Within these fields, particles emerge, interact, and vanish, weaving the fabric of reality as we know it. Today, we are honored to welcome an expert in this intricate and fascinating domain, Dr. Thomas Collis, a research associate in quantum field theory and theoretical cosmology at the DAMTP of University of Cambridge. Dr. Collis has traveled an extraordinary academic path. He began his journey at the prestigious, well, this would be a wrong pronunciation, École in Paris, expanded his research experience in Stanford, and collaborated with renowned Leonardo Senatore before joining the renowned DMTP at Cambridge. We extend a warm welcome to all our subscribers and viewers. Thank you for tuning as we explore the intriguing concepts of quantum field theory, and let us welcome Dr. Thomas Collis. Welcome, Doctor.
Hi, thank you so much for the invitation.
You're absolutely welcome. Just to tell the viewers also that we at Thomas are actually, very good friends, and we become a friend not on physics or mathematics, but on a different topic, which we will take it forward. Well, Dr. Thomas, a very warm welcome, and we already got some hello, sir, coming from Raghav.
Hi, Raghav. Nice
Yeah,
to meet you.
and also a very good friend of mine from Ottawa, and he's from Canada. All of the people are already there. So we will start today's podcast, but first of all, I would like to ask Thomas that, tell us, Dr. Thomas, that what was the basic idea that invoked that interest to take up quantum field theory?
So for me, the origin of my motivation to work in this field was when I was an undergrad student. I was taking a first course on cosmology, and for the first time, someone talked to me about the theory of inflation. So it's a theory that aims at describing the very early universe, pretty much the first second after the Big Bang. And I found it fascinating. Like, the basic idea behind this theory is that in a very short amount of time, a tiny fraction of a second, the universe expanded by an enormous amount from very microscopic scale to pretty much the size it has today. And I couldn't believe how such a thing was even possible. And it completely drives me crazy. It really motivated me to continue in research, learn the tools we need to understand this theory, which are quantum mechanics, general relativity, quantum field theory, and go on into that direction. And this is how I ended up doing research in the field of primordial cosmology. So that's a bit the origin of my interest for this topic.
That's wonderful. So if I may ask you, I hope you won't take me wrong, that your family, I mean to say, deep research into quantum field theory, which involves a lot of intricate and complex mathematics. Your family, your parents or your father, are they involved in any kind of mathematics or teaching or related to science disciplines?
Yeah, so that's a good question. So in fact, both of my parents are engineers in south of France, in Toulouse. They work for the aircraft industry. And my father did a PhD in physics. So in my family, we had a bit of scientific background, but he was not working in academia. He was not a professor. So they have encouraged me to continue studies in like natural science, but they had a bit of knowledge about what was research, but they are not directly related to academia.
There was, there was a lot of motivation in terms of that. So just to ask you, we will start with the technical discussions. How was how was your concept of mathematics from childhood, which now took an abrupt turn in one of the best universities of the world, Cambridge? Were you fearful? Were you thinking that, no, this is not my cup of tea? And how things actually evolved in getting into this amount of complex mathematics?
That's a very good question. So I think when I was a kid, I was good at school. So I was like fine with math. I liked them. I had good grades. So it was something that I quite liked. And then I arrived at university and I was still okay. But then at some point, I entered this École Normale Supérieure in Paris, where people that do math are really seriously doing math. And then I realized that it was one step further of my knowledge. So I realized that I couldn't be able to keep track of what was going on. And then I think I started to fear a bit the math when I was an undergrad student. And it took time to like feel confident again. And no, it's better, but it took me a while before finding some good way to get into math again. And so I pretty much, this is what we will see in the discussion, I think I pretty much prefer when we try to keep as many physical insight as we can and avoid technicality whenever we can.
Right, okay. So we will move into that. So that was how your childhood and your motivation for mathematics began. We have got one question which is coming up right now. We have yet to start the flow of the podcast, but we can take this question. And the name is I am Vengeance. I don't know the name. The wave equation function for Schrodinger equation collapses due to the observation we make. What if it was due to some other reason that we have not yet understand? I'm actually a mathematician.
Okay. We start with a very profound and deep question, which is, I think, very central to the development probably of physics and mathematics in the future, because at the moment, the way quantum mechanics work is based on postulate, that is that whenever we make a measurement, there is a collapse of the object that is describing the system into the finite outcome of this measurement. So this is what we call the collapse of the wave function, or the Born rule. And that is crucial and central in our current description of quantum mechanics. Some would say that it's a matter of, that's the rule, and then we can find interpretation of it, try to understand it, such as the Copenhagen interpretation or the many-word interpretation, which are different ways to make sense of this idea of collapse of the wave function. But some other people would eventually argue that quantum mechanics is not a fixed field of research, that it can still evolve, and eventually we have not yet understood the profound nature of what is the measurement or the collapse of the wave function. And there are some very interesting ideas these days related to the research in non-equilibrium quantum field theory that aims at explaining the measurement problem as a sort of non-equilibrium phenomena that will lead you to a definite outcome through a set of selection processes. So eventually, there are physical ways to go beyond this idea. And I think what is the most important thing to remember of this is the idea that nor quantum mechanics, nor general relativity or quantum field theory are settled topics. They are still evolving depending on what we understand and what we learn. And I hope it's a good encouragement for any students that are listening to pursue research in this field.
Absolutely. Thank you, Dr. Thomas. That was a very clean and yet very, very, very clear understanding of that. We come to the next question, Dr. Thomas, that we know that quantum field theory is different from classical mechanics and quantum mechanics in terms of describing particles and forces. So we would like to know from you that what are the factors and how does it differ from classical mechanics and quantum mechanics in describing the particles and forces?
Yes, thank you for the question. So when you send me the list of questions from last week, this was the first question on the list, and I felt a bit embarrassed because I realized that even if I'm doing quantum fields every day in my life, I didn't have a very clear and neat explanation to provide to everyone of what is a quantum field theory. And so, I feel a bit ashamed. But then I started to think about it, and I might have things to say. But just before we start, I think it's important so everyone knows that I'm a cosmologist mostly. I use quantum field theory in my daily basis as a theoretical cosmologist. I have a background in quantum optics and condensed matter, but I don't have a very good training in particle physics. So all the answers I will provide are within this framework of using quantum field theory to understand mostly cosmology. So that's for the background. Then this question of quantum field theory and how it departs from classical or quantum mechanics, I think the most important aspect to understand is the idea that quantum field theory is related to the possibility we can, at every point of space and time, create excitation. This excitation, for instance, you imagine a cavity in a lab in which you generate photons that travel in it. The fact that you create a photon in the cavity is what we call the creation of an excitation. If the photons eventually escape of the cavity, we say that we have annihilated the excitation. So we can create excitation, and these excitations have properties. They can have a mass, a spin, a charge. And there are two things I would like to stress is that these excitations, they don't necessarily have to describe fundamental particles. For instance, if I hit the table with my hand, it will create ripples like this that we call phonons, and they are excitation of matter that are not fundamental particles. Still, they can be described by a field theory. And the second aspect that is important is that this excitation, they don't have to be quantum necessarily. For instance, we can describe the appearance of cluster of dark matter in the universe to describe the emergence of structure. That is described by a field theory. That can be thought as an excitation or an inhomogeneity, but that is not a quantum object. So field theories are these theories that describe the appearance of this excitation. A field is the object that tells you how lucky you are to have a given excitation of a given nature at a point in space and time. And then a field theory will be the theory that tells you how this field evolves, and so how you have this collective creation of excitation that move across space and time. And so that's the fundamental description we will use.
Okay, thank you very much. So that was a very, very clear understanding. We have got a question. I think this is absolutely from what you are willing to talk about the cosmology part. Tausif Parvez is asking, QFT is such a vast subject. Before diving into research, we don't quite get to learn a lot of it. I want to know how much QFT does one need to know in order to start doing research in BH, I think black hole evaporation.
Black hole evaporation. Okay. So that's a good question, and I think it's important to realize that when we start to do research, it's normal that we don't know anything about a topic, and you will gradually learn new things. And I think that every physicist on Earth are still learning new things every day. So it's okay not knowing anything everything on a topic. Then what is important is to have someone that can supervise you and that can help you in the journey of learning these new things that you need. For instance, if you want to learn black hole evaporation, it's a very big topic that probably will take you years to know everything about it. And I don't think that there is anyone on Earth, in fact, that fully understands everything about this thing. But so this is why I think it's important that you enter in contact with someone in your area that will help you to go through this learning. And then just if you want some basic guidance, if you want to learn about black hole, you need to learn a bit of general relativity. Black hole evaporation is a very interesting topic that was developed, in fact, partly in Cambridge, mostly around Stephen Hawking. And as you know, historically, this is one of the first places where we have started to combine quantum mechanics and general relativity. So if you want to learn black hole evaporation, on the top of general relativity, I would also strongly recommend to have a strong background in quantum mechanics. And then I think you can start to work. When you have the basics in general relativity and the basics in quantum mechanics, probably you can start gradually to learn how to combine them and study black hole evaporation. But keep in mind that it will be a long process. I hope it helps.
Yeah, so Tausif, you got a clear path from Dr. Thomas that what are the things that you need to learn. Doctor, my next question is that when we are talking about the role of quantum field theory in cosmology, what makes me wonderful is that, Tausif has told thank you. So thank you, Dr. Thomas, for the answer. Yeah. So we could have used other theories, I mean to say, for example, cosmology as part of general relativity or classical cosmology. So my question is that what is the role of QFT in describing early universe, particularly during the inflationary period? And most importantly, why we are using QFT and not any other theory? I mean, so what is the significance of that?
Yeah, so that's a good question because, in fact, nothing nothing precludes us to use classical field theory to describe what was going on in the early universe. And in fact, the current paradigm is that the origin of the fluctuation we observe in the universe, that means the origin of all the structure we today observe in the universe, such as galaxies, clusters of galaxies, voids, filaments, all those things originate from quantum fluctuation of the primordial vacuum that were created during this early phase of inflation, just after the Big Bang. And in this idea, it's very fascinating because we say that all the structure really originates from quantum fluctuation. It's an approach that has been predicted by the first inflationary model that were written down in the 80s. That means if you assume that in the early universe, there is what we call a scalar field, which is one of those fields that create excitation that is present in the early universe, then it will generate this fluctuation. And this fluctuation will leave imprint on the sky. And since this prediction, this is precisely what we have observed so far. So this prediction of having quantum fields generating fluctuation that we later on observe in the universe is an extremely well-tested framework. So it's a very strong prediction. Yet, it doesn't mean that you cannot have created this excitation from a classical theory, for instance, from a thermal bath. This is typically what happened in some alternatives to the main framework of inflation, such as bouncing universe that we call ekpyrosis model, where the universe first contracts, then reach a bounce and expand again, or what can happen in the context of what we call warm inflation. So the main paradigm is that the structure comes from quantum fluctuation, but still there exist alternatives that are classical.
Yeah, I got it. That is very clear. Now, I have got a question again from one of the subscribers. Before that, Dr. Thomas, I want to understand, as you rightly told at the beginning, that you specialize in QFT in cosmology. Now, say, for example, if you can give us an idea, what I'm trying to understand is that, for example, Dirac equation. It is a relativistic wave equation. Now, there are people who works with Dirac equation, little bit related to particle physics, etc. People works in cosmology. So, I mean to say, there are various areas of specialization on the general idea of QFT. What are the areas that actually are diverging from if I take the central point of QFT, what are the areas that people work on research?
Ooh. So I don't know if I'm the most competent person to answer this question. So as you see, I'm relatively young, and so I have a bad historical background on the evolution of this field at large. But maybe I can give a few just perspectives. So first of all, there are people that work from QFT on particle physics. For instance, they work on collider experiments. They try to understand what we do when we construct big particle physics collider. What is the standard model of particle physics? What are its possible extensions? And this is a very big field of research. Then there are people just as me that work on cosmology, which is what are the implications of quantum field theory in the evolution of the universe? What are the role played by particles in primordial cosmology, in the late universe, through the emergence of dark energy and dark matter? And that's another field of research. And I would say that there is a third direction that is extremely important also, that is more related to what people do in condensed matter, and that is related to creating small-scale experiments in the lab that we can explain through quantum field theory techniques. This is also a very fascinating field of research in the sense that there are many exotic phenomena that we can create in laboratories that are very complicated to explain from theoretical standpoints, and that really helping us to go beyond our current understanding of particle physics and cosmology. So I would say that these are three categories of direction of research in quantum field theory, but I think it's maybe very reductive to describe them in this sense, probably.
Thank you very much. So we come to the next question. He's asking, I'm Vengeance. I want to ask this to any physicists. Do each and every physicist embark on thought experiments like Einstein did? What if you get stuck in between and you don't have any ideas like Einstein and GR?
Yes. So I think that's a fair question, a good question. So thought experiments are useful in the sense that they allow us to have a simplistic framework where we can understand what's going on. So I think that theoretical physicists are often using thought experiments, or sometimes what we call toy model, to understand in a simpler way what was going on. Because when you look around you, reality is very complicated. But I think it's also important, depending on your taste, to keep an eye on what people are doing on the observational side of things. Because precisely when you get stuck in these thought experiments with no idea on where to go, they can provide you guidance. For instance, you might not necessarily be able to answer some question in the future just because of the fact that we won't have enough experimental guidance to tell which is the way to answer a question. This is why it's important to keep an eye on experimental guidance, especially when we feel a bit stuck on this like thought experiments. I hope it helps.
Absolutely, it answers, absolutely. So the same person is asking, I know that Claudia de Ram, a cosmologist, says we need to find at a finite distance gravity, but when we quantize it, if we can, does it definitely be finite or be infinite like electromagnetic field?
Sorry, let me think about the question. In fact, I don't know. I should ask her because like we collaborated with Claudia in the past. We work an article together on bouncing cosmology and how quantum information techniques can help us to distinguish this kind of bouncing cosmology from inflation. But we never discussed together about really this deep question about the nature of gravity. And in fact, I don't really know. So I'm not sure I really understand precisely what is meant by the question. And so I don't say mistake about what Claudia wanted to say. I don't want to commit into this one. It's fine. Sorry about it.
Yeah, absolutely. Now, when we read about quantum field theories, one part which comes very important is renormalization. I'm going to say, the physicist, we never enjoy infinite quantities or something, so we need to renormalize. Now, my question to you, Dr. Thomas, is that do this renormalization also plays an important role in cosmology?
Yes, so renormalization is quite crucial because it's a tool that allows us as physicists to understand how we change scale when we describe a physical phenomena. For instance, you understand that when you look at water, depending on the scale at which you look at it, you don't need to describe the same physics. If you look at it from very close, you need to describe the interaction between water molecules. If we look it from a bit further away, you need to describe a fluid. And if you look at it from even further away, what will eventually only matter are, for instance, the ocean waves in the deep water regime. So depending on the scale at which you look at a problem, you don't need the same physics to describe it. And renormalization, in particular, what we call the renormalization group, is the set of techniques that is used to understand this zoom in, zoom out on a physical theory. And you can imagine that it's quite crucial to understand these techniques in cosmology, because cosmology is precisely the field where wavelength, everything is moving with time and changing. And this is why it's quite crucial to understand how things that were initially microscopic ends up being gigantic after a duration of time in the universe. Therefore, these renormalization group techniques, they are very crucial for cosmologists. And to be honest, I don't think we have yet really accurately understand their full extent or what they are useful for in cosmology. For instance, at the moment, we work on using these techniques to better understand the field of research for the primordial universe that is known as stochastic inflation. And we think this renormalization technique will really help us to better understand that.
Thank you for the answer. Now, when we talk, I was just talking to you about Dirac equation. That was the first proven equation that united special relativity and quantum mechanics together. Now, what I'm trying to make a point over here is that this unison of two pillars, I mean to say, classical special relativity and the relativistic quantum mechanics, this was quite beautifully done with Dirac equation. After that, you were doing in cosmology, trying to understand how at the minute level the particles interact. Now, are there still any, I would say, research work going on other than quantization of gravity, where physicists are still looking to unite something with something at the very big with the very small with the help of quantum field theory mathematics? Or we are all done?
No, I think unification is a very vast field of research, and I would connect it from my personal perspective to what we call effective field theories, which are attempts to focus on what we really observed when we construct an experiment. So when we do physics, it's important that we don't keep the details of everything. We want to understand what are the relevant approximations we can make, what are the scales that are important, and the goal of the toolbox to achieve that are the set of techniques that we call effective field theories. What is nice with effective field theories is that they they aim at starting from a well understood theory and systematizing its extension, trying to understand how, when we start with some success, we extend it in a systematic manner using symmetries or physical principle or scale hierarchies. And I think this is an important route toward the idea of unification, is that starting on what we understand today, which are the standard models of particle physics and the standard model of cosmology, and understand how we can extend it. And hopefully this is the way we will gradually learn knowledge and in a unified manner, I would say. So that's this attempt of simplicity we look for with effective field theories.
Thank you for the answer. What I would also like to understand from you, Dr. Thomas, is that Dirac equation actually predicted what is called antimatter, which Paul Dirac thought that he was making a mistake in his equation, but later. So this matter and antimatter, does it play a very important role in understanding the early universe? How does it help us in providing better insights?
Yeah, I guess it depends a bit on which flavor of early universe you are working on. For instance, on my side, when I work on inflation, I work with what we call bosons, or fields that are scalar fields, which are their own antimatters, so that don't play a very important role. But if you look at an era that is a bit after inflation, that we call Big Bang nucleosynthesis, between the end of inflation and this time, you should have something that happened that we call the matter-antimatter asymmetry. Or if you want, the fact that not all the particles exactly annihilated with their antiparticles, and that explains why our universe is not empty today, but still has matter in it. And in fact, this is very likely that it happened because it only depends on the fact that a tiny fraction of the matter did not annihilated with the antimatter, and that was crucial in explaining the appearance of all the matter we today observe in the universe. So this field of research is very important. And I think it's called baryogenesis. I'm not an expert on it, but it's a very fascinating topic also.
Thank you very much. I will come to the rest of the questions, but before that, a very pertinent question, which I think all the viewers would like to listen from you, is that given the understanding the complexities of mathematics which are involved in quantum field theory, you're the right person. You're from one of the, I would say not one of the best university in the world, from DAMTP. Can you give us a simple but kind of a roadmap that what would be the process of mathematics, the basics, and then step by step, how to go about, say, for example, if somebody who has just gone through the graduation, taking up with an aim, say, for example, in your field only, quantum field theory and cosmology, what are the basics, what are the advancements, what is the physics, and in which area a person would get stuck and frustrated, and what would be the roadmap to clear that? I think this would be something very helpful. How to learn quantum field theory. Over to you, Dr. Thomas.
Okay, that's again quite a broad question, and I think it's also important to realize that you can have many different entry doors to this field, and you don't necessarily have to follow the traditional path, which I would say would be through particle physics training to enter the field of quantum field theory. There are several entry doors. Mine has been through first learning the interplay between primordial cosmology and first quantum mechanics, and then gradually realizing that if I wanted to understand this interplay between early universe and quantum mechanics, I had to learn quantum field theory. But I learned it not straight from the beginning. It was a gradual learning process. And so I think in terms of techniques that you can be frustrated if you don't have them to understand what was going on, the most important one, in my opinion, is what we call perturbation theory. Because perturbation theory is the physical approach that is also strongly based on math of understanding how we make approximation when we have a small parameter. And as I told you before, in my opinion, what is the most important aspect of physics is to understand what are the details that we can neglect. Therefore, it's important to understand how you do perturbation theory, to understand precisely what are the rules to construct a self-consistent theory while giving away some details. That is the first thing I would like to recommend for people. And the second thing is that I would first recommend to learn classical field theory, in the sense that many of the techniques that we use in quantum field theory are also used in, for instance, statistical physics, statistical field theory. And it also avoids to enter in some of the complication of quantum theory while keeping most of the important aspects. For instance, you can study renormalization in a classical field theory. This is, for instance, the case when we study the effective field theory of the large-scale structure, which describes the clustering of matter to create galaxies. So that would be my two advice for someone that would like to learn quantum field theory. First, study very well perturbation theory, and then start by classical field theory.
Okay, so first would be perturbation theory, and then would be the classical field theory. Can you suggest which book? I mean to say, just to ask, which book do you consider as your Bible in the guide?
That's a good question. I thought about it just before our discussion, and I realized that for quantum field theory, I have a book that I like. That is the one called Quantum Field Theory and the Standard Model by Schwartz. Maybe I can share the link. I don't know if it works if I share it there, but that's the book I would like to recommend, Quantum Field Theory and the Standard Model by Dr. Schwartz. I think it's a very pedagogical book to learn about quantum field theory. Yet I'm not sure it captures.
I will just share the in the chat box so that people can watch it. Just a second. I think, yeah. This is the link. So just to tell before Dr. Thomas proceeds, this is the link which you can click. It is available in cambridge.org. Its name is Quantum Field Theory and the Standard Model by Matthew D. Schwartz. Right, over to you. Yeah, please.
Thanks. But this is a very traditional ways of approaching quantum field theory. And I think it lacks a bit the other aspects of the problem that I mentioned before, the fact that quantum field theory can also be approached from the perspective of condensed matter. And so I think that another book I would like to recommend, but that is maybe a bit more advanced, is the book by Alex Kamenev that is called Field Theory for Non-Equilibrium System, that I will also share here, which is providing the other perspective on this problem, the one that is more related to statistical field theory, how we understand statistical systems, phase transition, condensed matter system. And I think the two of them provide a good view, but probably the second book is much more advanced than the first one. So I feel a bit ashamed that I don't have a nice reference that is more
No,
easy
that's
to
fine.
start.
These two will absolutely do that. So for first one, and now this one is actually Field Theory of Non-Equilibrium System, University of Minnesota by Alex Kamenev. Now, these are extremely important for these people who wants to understand, and Dr. Thomas is right away giving his best recommendations. That's wonderful. That's thank you. If I talk of I know it would be a very unwise question to ask, but still to ask you that what would be the prime focus in terms of, if I consider the mathematical knowledge, and you might say, Shaunak, there's a huge amount of mathematics involved, but still I would like to request you if you can pinpoint that what would be the core mathematical skill that a researcher needs for QFT.
I need to think a bit about it because being myself not so skilled in math, I don't know. Like, to be honest, I think it's important to realize that, as we said, the field of quantum field theory is broad, and I think there is space for everyone, in the sense that it's important that we have very skilled people that are extremely good at doing math because they help us to formalize the theory, to better understand what are its extensions. And so, for instance, if you are very good at doing differential geometry, group theory, then you have room to work in field theory. But if you are bad with these tools and still are good at having physical intuition or being interested in physical system, then there is also room for you. And I think you can also serve this field in a different manner. Probably you will never be good at doing this mathematical formulation of quantum field theory, but still I think you can be useful for it. But after, it's true that you need a minimal background in math to do this kind of thing. But I'm not sure this background in math is necessarily very high, depending on what you want to do. I think you need a bit of linear algebra, a bit, I guess, to have some good background in analysis. For instance, vectorial analysis is very useful. And I think you need to have done a bit of general relativity to be familiar with how to work with tensors. But apart from this, it should be fine. And so you shouldn't be worried not having the mathematical background. I think you should try to go on and learn the physics, and that will work.
Thank you very much. So we have come almost at the middle of our podcast and waiting for more questions from the subscribers. But before they ask you, I would like to ask now, the type of calculations and the visualizations that you do are something, I mean to say, you cannot see it on a practical sense. So, primordial black holes or cosmological things. So my question is that, do you use softwares or, I mean to say, simulations, in any case, to give you a kind of a feel-good factor that how these things will actually emerge into, possibly we can trace back to the time of Big Bang. So how do you actually do that?
And that's a good question. So we have a variety of quantities that we like to compute as theorists because they allow us they inform us about how our theory looks like. But very often these quantities are a bit abstract for people that don't work in that kind of field. These quantities that I'm talking about, they are what we call correlators or endpoint function. And in the statistical sense, they describe what we call the mean of a scalar field, the variance, that is how it fluctuates over space and time, the skewness, that is its distribution Gaussian or non-Gaussian, and so on. And this kind of measure, I agree with you, they are not so easy to visualize. But when we give them to some people that are doing observational cosmology, in general, they know how to interpret these quantities, the mean, the variance, the skewness, and they know how to use them to construct visualizations they can really compare to the data they have when they look at, for instance, the sky using a telescope or a satellite. So it's good that we have found quantities that allow us to be the middle ground between theorists and people that do observation. But on the job of translating these quantities to something that is very visual and that everyone can understand, on my side, I don't know how to do it, because what I do in general is to give these quantities to the people that do observational cosmology, and that will be their role to find the translation to real-world observation, for instance.
Okay, that's clears the doubt I mean to say, how these things are actually done. So, Dr. Thomas, at Cambridge, what is the research that you're doing? I mean to say, not in a very technical manner, but if you can tell our viewers that what exactly you are aiming to do, and what are the expectations out of this?
Yes, so as I told you, I'm mostly working in primordial cosmology, trying to use techniques that come from condensed matter and quantum optics to better understand what was going on in the early universe. And the attempt for doing so is some observation we made recently with colleagues, is that eventually the techniques we were using in the past to describe primordial cosmology are not really enough to describe the peculiarity of cosmology. That is, many of these techniques were imported from particle physics. And there is a fundamental difference between particle physics and cosmology, which is the fact that in cosmology, energy is not conserved. So if we want to understand this aspect, we need to develop new techniques, and we believe that these techniques can come from condensed matter and quantum optics. So my goal is to extend the toolbox we have at our disposal as primordial cosmologists, based on the previous success, include new extension, and that hopefully will help us to have a better control on what makes cosmology so unique compared to, for instance, particle physics. So that's my goal at the moment.
Okay, great. And wishing you all the best in your future endeavors.
Thank you.
Yeah. Now, the thing is that as we see that there's a growing interest in quantum gravity as well as string theory. I mean to say, these are very, very growing fields, etc. Although there are a lot of, different opinions specifically about string theory. Now, how can QFT, we can integrate within these frameworks in order to understand the quantum structure of space-time at the level of cosmological scales?
Yeah, so that's again quite a big question and a challenging research program, I guess, which is how do we bridge between what I do on my daily basis that we call quantum field theory in space-time, which is a perturbative approach, to what people do when they do quantum gravity, which is a non-perturbative approach. Like, how do we make contact between these two fields? And I think it's a very challenging and important question that we shouldn't neglect. Like, it's our goal in the end to make this contact. So it's a very important question. Then what I would like to say is that quantum field theory in space-time, the techniques that I'm using, are very successfully representing the observation we have of the universe today. So somehow they should represent some limit or a more complicated theory that we call quantum gravity. And we want to understand what is, if you want, how quantum gravity is an embedding for this quantum field theory in space-time description. This is why effective field theory are useful, because in general, they allow us to organize this dialogue between the fundamental theory that we are not yet fully clear about, which is likely to be related to something like string theory, and what we today observe in the sky that is very well described by quantum field theory in space-time. So my hope is that by improving the effective field theory techniques we use, we better improve the dialogue between these two things. But it's not an easy task. It's more a long-run project. I hope someday we will manage.
Okay, thank you. Thank you very much for this. Just a few more questions before we wrap up. So the newly proposed, I mean to say, the extensions in terms of standard model of particle physics, understanding dark matter and dark energy, if you can explain that, because just before your podcast, we had Asta from Surrey University talking about dark matter and dark energy. Obviously, QFT must play a very important role. So how does it integrate into dark matter and dark energy?
Yeah, so that's, again, an enormous topic on which we could talk for hours. But just a few ideas. First, it's not sure that dark matter and dark energy might eventually be some simple fundamental constituents just as one particle. It might be something that is much more complicated than this. The second thing that I would like to say is that we already have a lot of observation and constraints about the nature of dark matter and dark energy. What we are lacking is a more fundamental description, but the effective description of dark matter and dark energy as sort of cosmological fluids that play a role on space-time is extensively constrained by data. And this sort of coarse-grained average description, if we want to understand it in terms of fundamental viewpoint, we need to better understand what is the articulation in cosmology between microphysical description, microphysical model, and the average description that we see at late time in the universe. And again, I come back to this point that I already mentioned, that our main task, in my opinion, today as cosmologists is to understand this articulation between microphysical description and long wavelength, coarse-grained, classical stochastic description. And this is precisely the attempt that we are trying to do by improving our effective field theory description for the universe.
Thomas, just for a second, be online. I will just disconnect and come back. I think there is an error which is showing. Maybe I am not being able to take the questions of the subscriber. So please do not connect. Just be there.
Sure. But thank you, everyone, for the question. And my apologies for my poor English. And what was the other thing I wanted to say?
Yeah, I think that we have got questions. As I told you, there was some kind of a problem. Okay, so before we wrap up, this question coming up from SSJ. Professor, what is the reason behind quantum tunneling? I never find out the sufficient answer to the question. So,
that's a good one also. So let me think if I can say anything useful that might help on this. Because in fact, I never directly work on quantum tunneling. So maybe I won't be the person with the more insight on it. But maybe to give you some ideas about it, it's important to realize that quantum theory is not a deterministic theory. It's a stochastic theory where things have chance to happen. Sometimes they have a very unlikely chance to happen, but still, from time to time, that can happen. For instance, imagine that you have a wall. It's very unlikely that you go through the wall. But in quantum mechanics, if there is a non-zero probability of you go through the wall and eventually wait long enough, then there is a chance that happens. And that is related to the fundamental nature of this theory, which is not a deterministic theory. It's really a stochastic theory. So I hope that this is, I think, the most important thing to keep in mind. And then the second aspect to realize is that the reason why for us, macroscopic person, we don't go through walls is that the chance that it happens is extremely suppressed. That the more you go to macroscopic object, the more this unlikely sort of event can happen. But when you go to the microscopic world, the rules are a bit different. And then the chance that a single, for instance, fundamental excitation goes through a wall is much more likely to happen. So I think that would be the way I would thought of quantum tunneling. The idea that quantum mechanics is a probabilistic theory where eventually unlikely event can happen. And the second thing is that when you go at microscopic enough scale, which means eventually very high energy, you increase your chances for this unlikely event to happen. I hope it helps, but it's a difficult question.
Yeah, absolutely. I'm so sorry that actually it was constantly showing a same kind of a figure. So there are questions which came up. I'm quickly taking one after that. Scientific Irfan is asking, as we know, normal ordered Hamiltonian must give zero energy when acting on the vacuum state or the ground state of the field. Then why quantum field like electromagnetic field has non-zero 0-point energy?
Yes, that's a very important question for cosmology, black holes, such as the black hole evaporation process. So thank you for asking it. The important aspect in this story is that eventually your Hamiltonian can be time dependent. And what it means in practice is that it's a process that we call the Schwinger effect, where when you have a classical field that is energetic enough, you can emit photons out of it. So it's what we call stimulated emission. And that can happen in the context of cosmology or black holes, where what plays the role of the classical field is the gravitational background. And this is why, even as you mentioned, if you work in flat space-time, nothing will happen and the vacuum will stay empty. But now, if there is a gravitational field that can play the role of a very strong gravitational background, then that can create pairs of fundamental quanta. And this is how, starting from an empty vacuum, you end up populating it with pairs of particles, pairs of quanta out of the vacuum. And mathematically, if you want to see it from your description, what is important is the fact that the Hamiltonian is time dependent, so it can change across time. So I hope it answers a bit the question.
Absolutely. Thank you very much. Abdul Halim is telling bonjour. Would it
Bonjour.
be possible? Would it be possible a short idea to development of gauge theory and QFT in curve space in your work?
Yes. So gauge theories are important for cosmologists or for particle physicists at large, in the sense that they allow us to describe particles that we need in order to describe physical phenomena. So we need gauge theory for our description of the world. And then there is this question of how we take the standard model gauge theory and apply it to cosmology. And that leads to an extremely rich field of research. For instance, the understanding of gauge theories in the context of inflation is enormous. There are so many things to say. You can have a much richer phenomenology than what was done in the past if you just consider a single scalar field. That is what we call gauge inflation, for instance. And we need to consider this gauge field in order to enrich our phenomenology, and it's something that we are currently working on. How do we use effective field theories that I talked about before in the presence of this gauge theory? And in fact, it's not easy. At the moment, we try to adapt this, and it's a long journey. So I hope it answers a bit the question.
Absolutely. This is a question I mean to say, Jason is asking, how do you incorporate dark matter and dark energy into the quantum field when we have no idea what they are? Seems illogical.
Yeah, that's a fair statement. Yeah, I think I would agree with this statement in the sense that incorporated a microphysical description of what is dark matter and dark energy seems relatively hopeless in the sense that we can construct quite a lot of models that can eventually achieve this task. This is why effective field theories are useful, because their goal is to take into account what we know and write down the uncertainty in a sort of systematic and parameterized manner based in our knowledge. For instance, if we have some symmetries that are at play, even if there is a part of the physics that we don't understand, this part of the physics that we don't understand cannot be whatever we want. And the same apply if you have, for instance, scale hierarchy, locality, unitarity, a set of physical principles that helps us to understand what is our uncertainty about the fundamental description of this theory. And this is why we can still make progress using quantum field theory and effective field theories, despite we don't know the precise nature of dark matter and dark energy.
Thank you. So before we close down, Dr. Thomas, just a different kind of a question. As a scientist and a researcher, you work with a lot of things which, I mean to say, you try to give a shape of certain things which are not certain. Now, as you went to the Faroe Island, which is, I mean, it's a beautiful nature, sea and mountain and ocean and birds all around. Don't you think at the end of the day that we all perceive the same nature, that beauty of Faroe Island, into the complexities of mathematics in a certain way? Do you still find nature and physics uniting into a cosmic dance where you can see things which you're working, ultimately trying to see the reality which is so beautiful in front of us?
Well, I guess it's a very personal question. For the comparison with the Faroe Island and the mathematics, maybe the dry weather and the fact that it's a rough weather with a lot of wind makes it comparable to math, that's for sure. Then for the more general perspective about what we do as theoretical physicists, given some vision of nature, the universe around us, yes, for me, it's part of the motivation. this fact that when I do physics, I forget about my condition of human being and just think that eventually the universe is bigger than us, that at the scale of the universe timeline, I'm very little. That's something that is bringing me peace and also motivation to go on, because it also tells me that what matters are only my action as a human being. And so, yes, doing cosmology is a way for me to get reassured about my place on Earth. So I like that.
So apart from doing mathematics at Cambridge and your studies, what are your hobbies and what do you do?
That's a good question. So my hobbies, I like to go climbing, either indoor or outdoor. I do a bit of guitar, and I traveled quite a lot between the UK and France to see my partner who is living in Paris. But in my free time, I also like outdoor activities, hiking and so on. And I also like indoor activities such as museum visit and restaurants.
That's wonderful. We have got one question. I think we can take that. Goat is asking, what about 4D de Sitter from string theory via 6D supergravity? Can we make positive cosmological constant?
Okay. So I guess that's a bit beyond my field of expertise, because I never worked in practice in what we call these compactification models, where we start from a theory that has more than 4 dimensions and wrap some of them in order to end up with a cosmological spacetime that has only 4 dimensions. And that seems to be a promising direction to explain some of the phenomena we observe, such as the emergence of a cosmological constant, but it has also tremendous challenges because it's extremely hard. But I think it comes back to one of the points I mentioned in the past, which is our role as cosmologists is to improve this dialogue between scale, how we go from this 11-dimension theory to our 4D dimension theory. And I think it's really crucial in the future that we improve this journey between very high energy description and low energy description of the world. And I think there is still space for improvement. For instance, this whole debate about compactification that is not settled yet is a proof that there is space for work in this field. And I encourage you to go into that direction if you like it.
To this through my mobile data, so I don't.
Don't worry. I was going through the chat on the YouTube to try to answer a couple of questions for those that are still
okay.
online.
So you have okay. So physics is like kung fu. It may take a lifetime to one area of expertise. That is true. As we have just seen win the Nobel Prize, is it better to learn physics or computer science?
Yeah, I answered this one briefly while you were away. But yeah, I guess it's a matter of taste.
Yes, please. I think there's a net problem going on.
Don't worry. I'm going back on the YouTube also to see the chat if there are other questions. So there was this question about the Dirac Sea and quantum field theory are the same. Okay, so maybe I can briefly answer this one. So I think they are not exactly the same, in the sense that the Dirac Sea was a proposal that was made by brilliant mathematician and physicist Paul Dirac in the 30s to provide an explanation for the dynamics of fermions. Yet I don't think it's a successful theory, in the sense that it was bumping into problems that led people to consider something bigger, and this something bigger is precisely the onset of quantum field theory. So if I remember my courses on history of physics correctly, quantum field theory are an attempt to go one step beyond the Dirac Sea attempt. And the idea to cure the problems about the Dirac Sea was precisely to introduce this idea that at every point of space and time, you can create quanta, or excitation, creation and annihilation operators that will create as many excitation as you want. And when you use that as the fundamental postulate to construct your quantum field theory, you don't need anymore to consider things such as the Dirac Sea. So I hope it answers the question. Maybe I lose Shunak again, but I'll see if there are other questions.
Okay, so that's nice. My net connection has been restored. I'm so feeling happy. So there's an acknowledgement. Thank you very much, Dr. Thomas. You're kind and simple. I really enjoyed having a chat with you. This is
thank you very much, everyone.
Yeah, he's telling that he is. Thank you very much for merci beaucoup pour vos responses. Okay, again, that is French.
Yes, so, yes. Merci pour les
yeah, so Thomas would be maybe teaching me French later, apart from quantum field theory.
Okay. Yeah, probably easier.
Yeah, absolutely.
Or maybe not. Easier. Maybe not, in fact. Not so sure in the end.
Okay, so thank you, Dr. Thomas, for a very long, but I think you also enjoyed with all these questions.
Yes, really much. And it's a hard exercise. I don't do much of outreach in my daily life. So I can appreciate the hard work that people are putting into it when I myself experience it and finding how hard it is sometimes to answer a simple question. So thank you everyone for the nice question.
His Highness is telling thank you for being a good shepherd.
Good luck.
Thank you. Any last minute advice before we close down, Dr. Thomas, to the young people aspiring who are willing to come up with quantum field theory?
Yes, so one word advice would be to keep confidence on yourself, because as we saw, there are so many things to learn that sometimes we can feel that we won't manage to go through it. But take it little by little and keep motivation, like keep things that are fascinating you. That will be the way that you will find strength to move forward little by little. But also manage your confidence. That is, find people around you that will help you to feel confident. It's important that you have people that encourage you to go through this. Otherwise, it will be too hard. So find supervisors that will help your confidence, find collaborators that will help your confidence, and take it one step at a time.
Thank you very much, Dr. Thomas, and a kind apologies to the subscribers and viewers. There was a net problem, and once I edit this live, everything will be very smooth, not a problem. So Dr. Thomas, very warm thanks, gratitude from my side, because I understand you're into research, a lot of things coming up, but almost 1 hour, 8 minutes of continuous talking, discussion on quantum field theory. I'm really thankful to you, and also, to all the viewers. So we will keep in touch with you, Dr. Thomas, that in future, when you proceed with your researches also, I would request you, with your permission, we can again conduct a podcast on similar areas on cosmology, etc. So that's it.
Absolutely. First, let me thank you very much for organizing all of this. That was a lot of work, and you've done it impressively well. The organization was perfect. The questions were perfect. So thank you so much for this. And thank you for everyone that watched this live video. It was very nice. Thank you for the question. And yeah, I hope we can do it again in the future.
Yeah, as I told you earlier, that my subscribers are extremely knowledgeable, well-read. The number of subscribers compared to popular channels of YouTube, it is less. But I'm extremely honored to get this subscriber base who asked always great relevant questions and making people like you, great researchers, feel comfortable. Not a kind of a generic question. So these questions really help us.
The questions were, in fact, very on point. I was impressed by the level of the questions. So that's great. I hope you can manage this community.
Yeah, absolutely.
Great people.
Absolutely. I will keep managing this community. And thank you very much, Dr. Thomas. Wishing you all the best for your future endeavors, and wish to see you soon. So let us not lose the
Sure. Thank you very much, Shunak. That was really a pleasure. Thank you.
Thank you. Thank you very much. And thank you to all the subscribers. Good night from India. And I think it will be good evening over to your UK.
Absolutely. See you, everyone. Thanks.
Yeah. Goodbye.